Welcome, this is Professor Ridge, and today's lesson 3.1, Functions and Function Notation. And our first learning objective for today is determine whether a relation represents a function. A relation is a set of ordered pairs. The set of the first components of each ordered pair is called the domain. Okay, so that's a key word here, domain. And the set of the second components of each ordered pair is called the range. Okay, so let's look at this example here. So we got this set of ordered pairs. The first number of each pair is the first natural numbers, first 5 natural numbers. So you got 1, 2, 3, 4, 5. And then the second number is just twice that of the first. So 1 times 2 is 2. 2 times 2 is 4. 3 times 2 is 6. 4 times 2 is 8. 5 times 2 is 10. Okay, so the domain will be the first numbers, right? The x's, if we think of it as x, y. So the domain is just the 1, 2, 3, 4, 5. And then the range is the second numbers. So the 2, the 4, the 3, 6, 8, 10. 2, 4, 6, 8, 10. Note that each value in the domain is also known as the input value. So a lot of times we refer to the first member of the ordered pair, the x. We call that the input value or the independent variable. Okay, and it's also labeled lowercase x because we think of ordered pair for math typically as we think of x, y. So the x would be your input value and the y would be your output value. So, and again, just to kind of reiterate this, so the input value is also called the independent variable. Output value, that's the y, and it's called the dependent variable. So you got the independent variables, your input, the dependent variables, your output. And then a function f is a relation that assigns a single value in the range to each value in the domain. In other words, no x values are repeated. So for our example that relates the first 5 natural numbers to numbers double their value, this relation is a function because each element of the domain, 1, 2, 3, 4, 5, is paired with exactly one element in the range, 2, 4, 6, 8, 10. So this way of assigning an output value for each of the input values, there's only one answer you're going to get. So 1, if we double it, there's only one answer. You're just going to get 2. And then for 2, you're just going to get one output, 4. Right? There's only one output. So that's key. Well, I'll write it down in a second. Okay, so a function is a relation in which each possible input value leads to exactly one output value. We say the output is a function of the input. The input value makes up the domain and the output value makes up the range. I like to just say it this way too. Every x gets exactly one y. So let me write that down. So again, every x value gets exactly one y value, right? So that's my short version of saying the same thing. Okay, state whether the relation is a function or not a function. So what we have here is 2 sets, and we're basically going to draw a diagram to how we relate things from the domain to the range with just an arrow. Actually, hang on. All right, so let's say 1 gets assigned to 7. So we just draw an arrow from 1 to 7. So that will represent the ordered pair 1, 7. 2 gets assigned to 12. And 3 gets assigned to 7. And notice that each member of the domain got paired with exactly or assigned to or matched or corresponds. You can use any of those words. Okay. So 1 corresponds to 7, or 1 is assigned to 7, or 1 is paired with 7, right? You can say any of those things. Okay, so each member of the domain is assigned exactly one value of the range, right? So one input value gets one output value in this case, or every input value gets assigned exactly one, right? Exactly one output value. So this is a relation. This is a function. So a relation is just the way you assign, make ordered pairs basically. And then a function is the special type of relation where each member of the domain gets exactly one member of the range. Okay, let's look at this one. We got 1, 2, 3 for the domain and just 7 for the range. And each member of the domain is going to be assigned 7. So hit pause for a second and think about your answer. So does this represent a function? Does this relation represent a function? Okay, and the answer is yes, because each member of the domain is assigned exactly one member of the range. Doesn't matter that they're all the same. Each member of the range of domain is getting exactly one member of the range. So that one's a function as well. All right, so let's look at this one. 5 goes to 2, 10 goes to 4, and 6, and 15 goes to 8. So does that represent a function? And again, pause to see if you can think of the answer. All right, so the answer is no, because if you look at 10, this member of the domain got assigned 2 values of the range. And again, the key is it has to get exactly one output value, right? So 10 violates that rule, so it got 2 members of the range. So the answer is no, it's not a function. Okay, let's look at example 1. Determine if the menu price lists are functions. The coffee shop menu shown below consists of items and their prices. A, is the price a function of the item? B, is the item a function of the price? Okay, so for A, is price a function of the item? So we want to know is price, and I forgot to mention this when we went over the input here. Right here, we say the output is a function of the input. So whatever the y values are, we're going to say that y value is a function. If it's a function, the output is a function of the input. So on this one, when we're saying is price, so we're saying that's the output, is price a function of the item? So here's how you identify if it's a relation. If the relation is a function, identify the input values. So the input values will be the items. So plain donut, jelly donut, chocolate donut. Identify the output values. So the output values would be the price, right? Because price is the output, input would be item. So price 149. So does so basically this is like our arrow diagram we just did. You can see the plain donut gets assigned exactly one price. Jelly donut gets assigned a price. And chocolate donut gets assigned price. And it's okay that those are the same prices because each input value is getting assigned exactly one output value. There's not 2 prices for a jelly donut depending on what day I'm asking or whatever. Okay, so this one, A, would be yes, right? So if each input value leads to only one output value, then the relationship's a function. So for A, this would be yes, it's a function. Okay, and then B, is item a function of price? So item's your output value. So basically, we're going to flip this around. It's like you have 149 and 199 as your domain, your input values. And so you don't have to write repeats. And then your range would be the items. So price, item. So the items would be the plain donut, I'll just write P, jelly donut, and chocolate donut. And so 149 is the plain donut, 199 is either the jelly donut or the chocolate donut. So this input value has two output values, so no, that's not a function. Example 2, determining if class grade rules are functions. In a particular math class, the overall percent grade corresponds to a grade point average. Is grade point average a function of the percent grade? Okay, so that's the A there, question. And then B, is the percent grade a function of the grade point average? So that's our question B. So let's see A. Grade point average, is that a function of percent? So grade point average would be the domain would be the percent grade, and then the range would be the grade point average. I'm just going to write GPA. Okay, so you could see, so we're going from percent to there. So you could see that no matter what percent grade, that the output value is only going to be one answer. So if you get any of these items, you're just going to get one answer, basically, right? Going that way. So if you think about it, if you did 0, 1, 2, 0 would be 0, 1 would be 0, 2 would be 0. So even though this represents a bunch of items, each individual item will get assigned to just 0.0. Same thing for this range, so on. Okay, so that one would be yes, that's a function. Right, so GPA is a function of percent grade. Okay, now the other way around. So we want to switch this. So GPA would be our domain, and the range would be your percent grade. And again, so for instance, if you got 0, well, let's do the 1.0. If you got a 1.0, there's a whole bunch of possibilities. You could have had a 57, you could have had a 58, you could have had a 59, so on, right? So for just this one, there will be several answers, right? Not just exactly one input. So this one is no, not a function. And you just have to find one example that breaks the rule, right? So if there's one input value that gets more than one output value, it's not a function. All right, so find the value of a function. And before we do that, we need to learn function notation. Okay, so this is really important, so I want to highlight this from the textbook here. To represent height is a function of age, we start by identifying descriptive variables h for height and a for age. The letters F, G, and H are often used to represent functions, just as we use X, Y, and Z represent numbers or variables, right? And capital A, B, and C to represent sets. So those are, kind of standards, but you're allowed to use any letter to represent any function, not just F, G, and H. But that's our common ones. Okay? So if I want to say H, which is height, is a function F of age, A, right, this up here, we're going to call the function F. The name of the function will be F, right? The height is the, H is the variable for how high your height, and A is your variable for your age. So h equals f of a. This is the notation that we're going to use. All right, so use the parentheses to indicate the function input. So the input is the whatever letter I put inside the parentheses. And you read this as f of a. So f of a. Right? So it's the long-winded version is the function f. Right? And then the input value is a. So f of a. Remember, we can only use letters to name the function. So the notation h of a shows us that h depends on a. The value a must be put into the function h to get a result. The parentheses indicate the age is the input of the function. They do not indicate multiplication, right? So that's important. And we can also give algebraic expressions as the input to a function. So for example, f of a plus b means first add a and b together, take that result and put it into the function f. Okay, the operations must be performed in this order to obtain the correct result. Okay, so function notation again. The notation y equals f of x defines a function named f. Okay, so this letter in front, that's the name of the function. Okay, this is read as y is a function of x. Y is a function of x. The letter x represents the input value. So the input value is in here, or the independent variable. The letter y, or f of x. Now this is a key thing. Remember, right here, this equation, y equals f of x. So a lot of times I'll ask my students, what does f of x mean? Right? And the short answer, it's a y value. F of x, right here. F of x is equal to y. So f of x is a y value. So the letter y, or f of x, see those are the same thing, represent the output value, or the dependent variable. So when I'm doing ordered pairs, if I'm using function notation, so if I have x, y is my ordered pair, but if I'm using function notation, my output value can be written as f of x, right? Because this is equal to y, right, from here. So that's important to understand that. I didn't understand that when I was a freshman in college, and later on I figured it out, and it made things so much easier when you're using this function notation. Okay, so example 3, using function notation for days in the month. Use function notation to represent a function whose input is the name of the month. So the input value, the x, is going to be months, January, February, March, so on. The output value is the number of days in that month. So assume that the domain does not include leap years. Okay, so our domain is going to be January, February, March, April, so on. Okay, I'm not going to write it, finish it. And then the range would be basically, the range would be, let's see, how many days and months? Well, it depends. You can have 30 days, you can have 31 days, and also 28 days. I should have wrote it in order, but that's okay. All right, so if I want to write, use function notation to represent a function whose input is the name of the month and the output is the number of days. So we're going to say days, that's the output value, is equal to the function of the input value would be months. Okay, so an example would be if I did f of September, that's going to be equal to, how many days are in September? Let's see, I believe that there's 30. So that'd be 30 days. And I just wanted to highlight this note from the book. Note that the inputs to a function do not have to be numbers. Function inputs can be names of people, labels of geometric objects, or any other element that determines some kind of output. Okay, so actually the outputs can't, same thing, right? You don't have to have numbers for domain or range. They can be anything, right? And then the relationships, how do you relate? That's why it's called a relationship. Items from one set to the other set, okay? And to become a function, remember, every input value can only have one output value. That's the key, okay? But in math, right, typically we're going to just deal with numbers. So however, most of the functions we will work with in this book will have numbers as both for the inputs and the outputs. Example 4, interpreting function notation. A function n equals f of y gives the number of police officers in a town in year y. So what does f of 2005 equals 300 represent? So remember, n is the output, right? So 300 is the output, which is n. So that's the number of police officers. So we're saying the number of police officers is 300 in the year. So the input value is the year 2005. Or if we want to write it, in the year 2005, there were 300 police officers. You could say it that way as well. Okay, so again, so in the year 2005, right, so input 2005, there were 300 police officers. That's the output in the town. Representing functions using tables. So given a table of input-output values, determine whether the table represents a function. So you're going to identify the input and the output. You're going to check to see if each input is paired with only one output value. If so, the table represents a function. All right, so looking at example 5, you see in table 6 here, we got 2, 5, and 8 as the input values. So there's, and then there's just a single number for 2. So basically, if you go back to our arrow diagrams, right, 2 is just going to get 1, 5 is going to get 1, 8 is going to get 1. So yeah, that's a function. Okay, table 7, -3, 0, 4. And again, we just have one output for each of these. So that one's a function. So this one's a function. And then here we got 1, and then we got 5 repeated here. So if we were to make our arrow diagram, we would just write 5 once, and then 5 would get assigned 2 different values. So that one would be no. So you're looking if you see any repeated input values or any repeated x's that get 2 different y values, that'd be like in our arrow diagram, 5 would get 2 different values, right? 2 and 4. So that'd be no, not a function. Finding input and output values of a function. So how to, given the formula for a function, evaluate. Substitute the input value in the formula with the value provided and then calculate the result. So example 6 here, we want to evaluate f of x equals x squared plus 3x minus 4. So we're given, you can call it this equation, right? It's telling you how to find y values given an x value. You can think of that. It's like a function rule, we say. Okay, so y value, which is f of x, is given by this formula, x squared plus 3x minus 4. So if I want to find a, I want to find evaluate f of x at, they should have told us x equals 2, right? Or evaluate f of 2. That's typically where you will see it. So f of 2 is equal to, you're going to substitute. My suggestion is put blank parentheses everywhere you see an x. And you're going to substitute 2 in for all the x's. So in all the blank parentheses. And then this also, with putting the parentheses, can help you not mess up because of order operation kind of issues. So 2 squared is 4. 3 times 2 is 6. And then 4 plus 6 is 10, minus 4 is 6. So the answer is 6 for A. B, you can also put in A, another variable in for x. So everywhere there's an x, we're going to leave a blank parenthesis, and then we're going to substitute in the given value, which is A, the input value. And then simplify it. Well, there's really nothing to do with this one. So it's just changing x's to a's. You can also put in an expression. So a plus h, we're going to put blank parentheses and make them a little bigger because I'm going to put in a plus h. So I take the x out, put in a plus h. Simplify it. Okay, this one can be simplified. So we get a squared plus, using the binomial, square of a binomial formula. So it's a squared plus 2ah plus h squared. Distribute the 3. So 3a plus 3h minus 4. Okay, and then that's your answer. I don't think there's any like terms here. So there we go. And then now evaluate D. Now evaluate f of a plus h, which was c, right? That's this part, minus f of a, which was b, all over h. So for D, we just did all the hard part. We figured out these, the top, basically. So let's see. I'm just going to write equals. So f of a plus h, we just worked out, was this mess. So a squared plus 2ah plus h squared minus, not minus, plus, sorry, 3a plus 3h minus 4. And then minus, now here's where a lot of people mess up. We're going to do f of a, you got to put that in parentheses. A squared plus 3a minus 4. Should have had some separation here, but okay. And then that whole thing over h. Now let's see, if we distribute this minus sign, we get a squared plus 2ah plus h squared plus 3a plus 3h minus 4. Okay, distribute the minus sign. Minus a squared minus 3a plus 4. Then the whole thing all over h. Okay, and then let's see, we can cancel the a squared with the minus a squared, the 3a with the minus 3a, and the minus 4 with the 4. And now notice all 3 of these leftover terms have an h in them, so I'm going to factor that h out, and we get 2a, and then we get plus h, and then we get plus 3, and that h that I just factored out will cancel that h on the bottom, and then I'm left with this expression. This is a very important formula here for calculus. This is what calculus, differential calculus, is based on. If you put the limit in front of this as h goes to 0, that's what we call a derivative. Okay, but we're not doing calculus, but this is the algebra part of it. So if you go on to calculus, you're going to be using that. We call that the difference quotient. Really important concept. Example 7, evaluate evaluating functions. Given the function h of p is equal to p squared plus 2p, evaluate h of 4. So again, remember, to evaluate a function, we're just going to take the input value and substitute it in. So the input value is 4, and it's going in for p. So we take all the p's out. Remember, I use this trick. Put a blank parenthesis for all the input variables. So in this case, it's p. So take all the p's out, put a blank parenthesis. We're going to plug in 4. So we substitute 4 for all those p's. And then we just calculate this using order operations. So 4 squared is 16. 2 times 4 is 8. And then we get 24. And that's our answer. So the y value, so not the y, this is the p, right? So the input value is 4, and the output value is 24. Okay, so a lot of times we can call this, we can say this is h and p is the input value. Example 8, solving functions. Given the function h of p is equal to p squared plus 2p, solve for h of p is equal to 3. Now, a common mistake is students will take this 3 and plug it in for p. That's not what this is asking. They're saying find p, figure out what input value gives you an output value. So the input value is p, the output value is 3. So what we're doing is we're taking this equation and solving it for p. But remember, h of p, there's two ways you can do it. You can take this equation and substitute 3 in for h of p, so you put 3 here. Or you can take this equation and substitute p squared plus 2p for h of p. So you can do it either way. So if we do it that way, I'm going to take the p squared plus 2p, which is h of p, right? I'm going to put this, here, let's do this. So you see that this and this are equal, right? So we can take h of p out and put in p squared plus 2p for the h of p. We're going to plug that. Since these are equal, we're going to plug that into there. Or you can take the 3 and plug it in for the h of p. Either way, you get the same equation, just the sides are switched. So it doesn't matter which way you think of it. So this is the way I'm going to think of it. I'm plugging in this for h of p, and I want to solve it. Well, this is a quadratic equation that we solved in last chapter. So you want to get it equal to 0. So subtract 3 from both sides, or the shortcut, you move it to the other side, change the sign. We want to factor it. Factors the 3 that subtract to 2. Oops. Factors the 3 that subtract to 2. Well, that's just 3 and 1. The bigger sign gets that middle one. The bigger factor gets the middle sign. And to get -3, these signs have to be opposites. And then set each of those equal to 0. And then solve. So this one will be, just remember, move it to the other side, change the sign. Oops, I almost forgot to change sign. I just said it. Okay, and then so you're subtracting 3 from both sides, right? Shortcuts, just move it, change sign. Same thing for this one. So p is 1. So we get 2 answers for p. So the solution set would be -3 or 1. Okay, and it's still a function, right? Because we're not saying that the input value had 2 output values. We're saying that if -3 is the input, it just has 3 as the output. If I put in 1, it gets 3. So that's like in the arrow diagram. We have -3, 1. Each of these are only going to 1 value, so that's okay. That's not a problem, right? Still a function. evaluating functions expressed in formulas. How to. Given a function in equation form, write its algebraic formula. So your first step, solve the equation and isolate the output value. So if your output value is y, you want to get y equals and then everything else. Okay. And then write the other side as an expression that it involves only the input value. So that's key. Use all the usual algebraic methods for solving equations, such as adding or subtracting the same quantity from both sides, multiplying or divide both sides of the equation by the same quantity. So basically your techniques for solving equations. Properties of equality. So example 9, express the relationship 2n plus 6p equals 12 as a function p equals f of n if possible. So we want to get p all by itself. So our first step is we're going to get rid of the 2n. So again, if you do the shortcut, you're going to subtract 2n from both sides. So the net result is it's going to go to the other side and the sign's going to change. So it becomes minus 2n. And then the last step, we just got to divide by 6 to get p by itself. So then we get p equals, if you want, you can split this up into two fractions. 12 divided by 6 is 2. And then negative 2 divided by 6 is, it just reduces to negative 1/3 n. So you can leave it like that. And then if we want to write p as a function of n, using function notation, we're going to write p as a function of n. So f of n is equal to 2 minus 1/3 n. Okay, one more note I want to point out. This book doesn't do it this way, but a lot of books, we can, if you want, you can name the function p. So instead of writing p as a function of n, we can just use p for f. So we could even call this p as a function of n, 2 minus 1/3 n. This is the way I normally would do it. This book likes to use f, f, g, h is your standard for your function notation, but this is really common in a lot of other books. So you might see something like this. Example 10, expressing the equation of a circle as a function. Does the equation x squared plus y squared equal 1 represent a function with x as the input and y as the output? If so, express the relationship as a function y equals f of x. Okay, so if we want to try to get y by itself, so we're going to subtract x squared. So we get y squared equals 1 minus x squared. Now here's the problem. If we square root both sides, we get y squared equals square root of, remember from what we talked about earlier, technically the square root of y squared would be the absolute value of y. So when we get y equals plus or minus the square root of 1 minus x squared. Okay, so we got to put the plus minus here. And then that tells us that, so if say y is 3, we're going to get two different answers for x. So y cannot, or actually, am I saying that backwards? I am saying that backwards. If we put in x is 3, for instance, y would get us, well actually it couldn't do 3, it has to be somewhere between, let's say if x was 1/3, y would give us two different answers. We'd get the plus 1, the positive 1 minus 1/3 squared, and then the minus 1. I'm not going to work that out. Okay, so this will give us two answers. So this is not a function. Okay, evaluating a function given in tabular form. Okay, so given a function represented by a table, identify specific output and input values. Find the given input in the row or column of input values. Identify the corresponding output value that's paired with that input value. Find the given output values in the row or column of the output values, noting every time that output value appears. And then identify the input values corresponding to the given output values. So evaluating and solving a tabular function. So evaluate g of 3. So remember, the input value is inside that parenthesis. This is our input. And we want to know what outputs with 3. So if we're looking at our table, the input's the top row. So we want to say here's 3. That number is g of 3, which is 7. So the output is 7. So g of 3 is equal to 7. Right? And that's it. That's for A. And then B, solve g of n is equal to 6. So g of n is equal to 6. So we're saying the input is n, which equals what, to give me an output equal to 6. So we look on the bottom row output table. Here's 6. Oh, there's 2. There's that answer. Here's 6. There's that answer. So we have 2 answers. So n is equal to 2 or 4. Okay, so you get 2 solutions to that equation. Finding function values from a graph. Okay, this is probably one of the more important skills from the last couple we did. Finding a function value from a graph. Given the graph in figure 4 here, evaluate f of 2. So remember, f of 2, remember that's a y value. Remember, this means the y value, here's the long-winded bit. It's the y value, right, which is your output value. You can say output or y value at the given, at or for, you can even say for, or when the input value is 2. So specifically here, actually, let me write it that way. Let me write it that way. So, because we're specifically saying y value when the x value or the input value equals 2. So that's the long-winded version of this notation. So it's real precise. So we want x is 2. So here's x is 2. We're going to go on the vertical line. Here's the point that has x is the y, 2 is the x value. What's the y value at that point? So the y value is 1. Okay, so the f of 2 is equal to 1. It's the y value when x equals 2. Okay, so that's your A. B, solve f of x is equal to 4. So again, we're saying what x values, so remember this f of x is a y value for a given x value. Okay, so what x values produce a y value, what x values give an output value or y value equal to 4. Okay, so the y value, is equal to 4. So on the y-axis, we go to 4 and think of this vertical line y equals 4. Let me move that right there. And where does it intersect? What x values, right, give you a y value? So if you look at this point, this is 3, 4. And this point is negative 1, 4. Right? So if the y value is 4, the x value could be negative 1, or the x value could be 3. So then our answer is, so x equals negative 1, or x equals 3. So you have two solutions for that one, looking at the graph. Okay, on to the next learning objective. Determine whether a function is one-to-one. A one-to-one function is a function in which each output value corresponds to exactly one input value. So to be a one-to-one function, it has to be a function to begin with. So every x gets one y. Remember my shortcut definition. And then to be one-to-one, you got to do it the other way around. Every y would get one x. So it's one-to-one. So if we think about our arrow diagrams we did, we'll just do the 1, 2, 3, 4, 5, 6. See, every x gets one y. That would make the function part. So that's a function. And then to check for one-to-one is, so first it has to be a function, and then for every x, then going the other way, every y gets one x. So this y gets one x, this y gets one x. So that's a one-to-one function. Okay? So determine whether the relationship is a one-to-one function. Is the area of a circle a function of its radius? If yes, is the function a one-to-one function? So first we got to check, is it a function? So if you recall, area of a circle is pi r squared. So if I want to know, is area a function of radius, the answer is yes, because if I plug in a number for r in here, I'm only going to get one answer. So that'll be yes, it's a function. Area is a function. Oops. Function of radius. And then B, if yes, is the function one-to-one. So let's work the other way. If I can get the r by itself and square root it, so let's see here. We're going to divide by pi. So a over pi equals r squared, and then we're going to square root it. So r equals the square root of a over that. But remember, we got to do plus or minus. But since this circle radius can only be a positive number, so then that we can throw out the minus part and say yes, it's a one-to-one function, because radius has to be positive, so you can throw out the negative here. So then yes, it's one-to-one, right? So that's the thing that we know. This is a physical object. It can only have a positive number for r. So yes, one-to-one. Okay, next learning objective, use the vertical line test to identify functions. Using the vertical line test. The vertical line test can be used to determine whether a graph represents a function. If we can draw any vertical line that intersects a graph more than once, then the graph does not define a function, because a function has only one output value for each input value. So if you recall, if I did a vertical line, this vertical line here, this red vertical line represents, so we're assuming that all these grid marks are 1, so this would be 1, 2, 3. This vertical line represents x equals 3, and you can see that x equals 3 would have two different y values, you know, if we were doing our arrow diagram, here's our domain, it would have two different y values. It would be whatever that number is, like 2 point something, and whatever that number is. Again, 2 point something. Oh, this one would be negative 2 point something. Okay, so here we get, okay, I'm just going to say that's negative 2.1. I don't know what it is exactly. And then that one is 2.9. Okay, so you can see that's not a function because you got one x value that gets two different y values. So a vertical line represents a specific x value, and if it hits the graph more than once, that's like one x value getting two different y values. So it's not a function. So same thing, okay, on this one, here's one example, x equals 3, it only gets one answer. But you got to imagine every vertical line and see that all of them are just going to hit the graph just once. So yes, this is a function. If you look at this one, hey, this one particular x value gets two different y values. So again, it's like this one. X equals 3 is that vertical line. It gets two different y values. So it'll be something like this one. Okay, applying the vertical line tests. Example 14. Which of the graphs in figure 9 represent a function y equals f of x? So again, we're going to think of a vertical line. And imagine when I sweep this across, see it hits once. So if every vertical line, each particular vertical line can hit the graph only once, then it's a function. So that one's a function. So that's a function. So function. Okay, if I do the vertical line again, you can see that that's going to just hit once at no matter what vertical line I pick, it will hit the graph just once. So that one's a function. Okay, and then C, well, right off the bat, you can see that if you look at the y-axis, which is a vertical line, that has two y-intercepts, so that's going to be not a function. So if I pick x equals -1, again, I get two y values. The graph hits that vertical line twice. So you just need one counterexample to say not a function. So if there's any one x value that gets more than one y value, it's not a function. So that's a vertical line test. Quick and easy way to tell if something's a function or not by looking at the graph. Using the horizontal line test, once we have determined that a graph defines a function, an easy way to determine if it's one-to-one function is use the horizontal line test. So draw horizontal lines through the graph. If any horizontal line intersects the graph more than once, then the graph does not represent a one-to-one function. So again, so a vertical line is a particular x value, and a horizontal line, this would represent x equals, what is that, 5? 1, 2, 3, 4, 5. Okay, you can see it hits the graph once. So that x gets just one, or that y gets just one x. So now we're checking, we already checked that each x gets one y, but now we're going to go the other way. Does each, going backwards, oops, if we have domain, and range, so now we're checking that if you have a y value, for instance, if y was 5, it only got one y value, one x value, sorry, which was like, what is that? 2 point something. I'll just say 2.3. Okay, but now, so we want to check that every x, to be one-to-one, every y has to have exactly one x. But look at this vertical line, or horizontal line. Right here, if x is 1, sorry, if y is 1, right? If y is 1, y equals 1, you see we got 1, 2, these would be the x values here, right? 3 x values. So if y is 1, it'd give me three different x values. So it's not 1-to-1. It's still a function, but it's not a 1-to-1 function. Okay, now this one, if we put a horizontal line, so the horizontal line represents a y value, and you can see it's just going to hit the line once. So every y value, no matter where it is, will hit the graph just once. This arrowhead goes forever, so if it's down here, it connect way outside what I have graphed here, but it would hit the line just one time. So yeah, that one is yes, it's a 1-to-1 function. So B is a 1-to-1 function. So not only is it just a function, it's a 1-to-1 function. Okay, so you got to test first to see if it's a function, then you do the horizontal line test to see if it's 1-to-1. And then the last learning objective is graph the functions listed in the library of functions. So these are what we call basic functions, identifying basic toolkit functions. These are things that you should know how to graph quickly, easily. The name for this first one is a constant function. So f of c, or f of x is equal to c, where c is a constant. So for instance, if f of x was equal to 2, no matter what your input value is, the output value would always be equal to 2. So your output function is always going to be 2. So this would be called a constant function. So if I put in x is -2, y is 2, plot it. -2, 2, 0, 2, 2, 2, 3, 2, 4, 2, and then you can draw the line, and it's a horizontal line. So this is a constant function, the graph's a horizontal line. The next function we should know is what we call the identity function, because your input value and your output value are the same. So f of x is equal to x, and if you just make a table, -2, the output's going to be -2. So x, y, x 0, 0, 2, 2. So 0, 0, 2, 2, 3, 3, 4, 4, -2, -2, so on. And you draw the line through it. Alright, the next one is the absolute value function. So f of x is the absolute value of x. So basically the name of the function is typically just the basic function. If you plug in x, what are you doing? Taking the absolute value. So we call that the absolute value function. And again, if you make a table, so -2, plug it in, absolute value of -2 is 2, 0, plug it in, absolute value of 0 is 0, 2, plug it in, absolute value of 2 is 2, plot those points, and we get this nice V. So you should know absolute value function, the graph is a V. All right, the next basic function is a quadratic. We also call this, again, from what I said before, if you plug in x, you're going to square it. You can call that a square function. It's also a polynomial function degree 2, depending on how we're viewing this. And the graph makes what we call a parabola. Okay, and if you plot points, -2 squared is 4, -1 squared is 1, 0 squared is 0, 1 squared is 1, 2 squared is 4, and if you plot a few more, you get that shape. But if you did like 0.5, it would be 0.25, so on. And just plot them, and you get this nice parabola shape. Okay, so that's our basic square function or quadratic function. Moving on to cubic, so f of x is x cubed, so you can also say this is the cube function, or cubic, or a polynomial degree 3. All right, so if again we make a table, -1 to the third power is -1, negative 0.5 cubed is negative 0.125, 0 cubed 0, 0.5 cubed is 1.25, 1 cubed is 1. So basically you just punch these values in your calculator, cube them, and then that's the output value. And then you plot it and you get this cubic shape. Okay, so that's what the parabola. If we were to go to 2 cubed is 8, so then this would be all the way up at 8. You can see that it goes up very quickly. And then the -2 would be down at -8. Okay, the next one you should know is a reciprocal function. So 1 over x, that's a reciprocal of x. And if you just punch this in, -2, 1 divided by -2 is -1/2, or -0.5 if you're using a calculator. -1, 1 over -1 is just -1. If you do -0.5, 1 over -0.5 is -2, right? Or if you think of it as -1/2, the reciprocal of that is -2, right? So that's the other way to think of it. So if I had -1/2 and did the reciprocal 1 over this, reciprocal would be -2. Okay? And then the same thing for this one, 1/2, the reciprocal will be 2. Reciprocal 1's 1. Reciprocal 2 is 1/2 or 0.5. And you get this shape, which is called a hyperbola. Okay? So that's your reciprocal function. And then if you square it, reciprocal squared, you get this shape. So notice the negatives, when you square it, become positive. So it flips over. And it's a little more pronounced curve here. And this going down to 0 quicker. Okay, so that's your reciprocal squared. You should know that one. And then the next function is square root function. So notice, right, x, square root of x. So it's square root function. And this is basically, if you take, well, we'll talk about inverses later in a later section. If we take the square root of 0 is 0, square root of 1 is 1, square root of 4 is 2. The next one would be square root of 9 would be 3. But you can also do the intermediate, right? Square root of 2 is about 1. Okay, square root of 2 is about 1.414. So you can see that's right there. Okay, and you get this nice, we call square root shape. Okay, and then the next one would be cube root. This is our last one actually, cube root. So same thing, -1, cube root of -1 is 1. You can just punch this in a calculator. Cube root of -0.125 is -0.5. 0, 0, 1, 1, 1, 1, I'm sorry, 0.125, 0.5 cube root of this. Now the next nice one would be if you did the cube root of 8 would be 2. And then if you did cube root of -8, that would be -2. And then the next nice one would be 27.3. But, you know, you can see that goes off here. But if I were to go to 8.2, this would hit 2 at 8. So right about there if I was to extend the graph. Okay? So you get this nice curved shape. If you blow up that first unit, I want to kind of point this out to you. So if you blow up that first unit, this shape, so if this is 1, 1, it's really kind of like that. Okay, so it's nice. I didn't do really well on that, but hopefully you get the idea, right? So it's that nice curved shape. That's a cube root, sorry, cube root. And I think, let's see here. Yes, that brings us to the end of today's lesson. So again, make sure you practice a whole bunch. do all the exercises or all the odd exercises, and I'll see you next time.